Hi, my name is Davi Castro Silva, and today I want to talk about classical and quantum polynomial Freiman-Rouge algorithms. And this is joint work with Srinivasa Arunachalam, Arpal Dutz, and Tom Gore. To talk about this, I first want to talk about the Freiman-Rouge theorem. And this is a cornerstone of additive combinatorics and has several applications to theoretical computer science. Intuitively, it says that sets exhibiting approximate combinatorial subgroup behavior must be algebraically structured. Uh, to give it more precisely, we will work on up over absolute GDN, the binary hypercube, though this is mostly for simplicity as the theorem holds much more generally. And the main definition here that we need is that of a subset. So for a set A inside the hypercube, define this A plus A as the set of all elements that can be obtained as the sum of two elements from the set A. And the first thing that one can ask about the subsets is about their size. It's very easy to see that the size of the subset A plus A is at least the size of the original set A, and at most the size of the set A squared divided by 2. And both of these inequalities can be attained at least up to lower order terms. So some examples to get some intuition. First, if A is a set of, say, the first k uh, basis vectors, E1 up to Ek, then A plus A will be just the set of all doubles here, Ei plus Ej, which has size about k squared divided by 2. So it will get like the upper bound here up to lower order terms. And this will be true not only for basis vectors, but for any linearly independent set of vectors. However, even more generally, if A is a random set whose size is slightly larger than the root of the size of the space, say 2 to the 0.51 times n, then A plus A will contain essentially all of the space after to the n with very high probability. And so this will also get close to the upper bound here. For the lower bound, we can think of the case where A is a subspace V of FGDN. Then, by taking some sets, you cannot get outside of the subspace. So again, you guess that A plus A is equal to V, which will have the same size of A. And so we get the lower bound. And a bit more generally, if A is not a subspace, but it's dense inside a subspace, say it has size at least the size of the subspace V divided by K, some constant K, then A plus A still cannot get outside of the subspace V that contains it. So the size of A plus A is at most the K times the size of A. And here in these examples, and also more generally, we can think of sets having small doubling constants, where doubling constant is just the size of the subset divided by the size of the original set, as being almost closed on their addition. That's why they have doubling constant small, essentially. And in other words, we can think of the doubling constants k as giving a combinatorial measure of subgroup behavior. So if we are close to the lower bound here, then we are almost close in the addition. So this gives like a combinatorial measure that you are close to being a subgroup. While if you are close to the upper bound, then you are very far away from being a subgroup, essentially. And so going back to the examples that I had before, if A is additively independent, so meaning either like linearly independent or random, then the size of the subset will be close to the maximum size. And in particular, you shouldn't expect there to be any possible classification of sets that satisfy something close to the upper bound, because a random set will satisfy it. However, on the other side of the spectrum here, if it's closer to the lower bound, then there is a lot more structure, because like the main example here is that if A has density 1 over K, where K is a constant, inside a subspace V, then A plus A will have size at most K times the size of A. So like the doubling constant will be at most K. And the Freeman-Rouge theorem essentially shows that this last example is the only possibility. So it says that will have small doubling constant k if and only if you are dense inside a subspace V. More precisely, the Freiman-Ruja theorem says the following. If the size of the subset K is at most K times the size of the original set, then this set A is contained inside a subspace V whose size is not much larger than the size of the set A itself. So it's at most some exponential in the doubling constant K times the size of A. And this will be a constant if K is a constant. And so this theorem is extremely useful, but the exponential dependence sometimes leads to poor quantitative bounds. However, the exponential dependence is necessary. The optimal bound is known, and it's about 4 to the k divided by 2k. And actually, I can show you an example where this upper bound is essentially attained. So in this example, the set A we consider is that's where we have all of the bit strings, where on the first k coordinates you have only 1, 1, and the rest is 0, while on the last n minus k coordinates you can't have anything. So it's written like this. And then a simple computation shows that the size of A plus A will be k divided by 2 times the size of A, where k is like the size here, the number of elements of the basis vectors that you take here. But the span of A, meaning like the smallest subspace that contains the set A, is the whole space F2 to the n itself, because this set A generates the F2 to the n. And so you get the doubling constant 2 to the k divided by, you have that the size of the span is 2 to the k divided by k, and the doubling constant is k over 2. So this is an exponential dependency in the doubling constant. However, in this case, we can say something more. So like A, while it's not inside a small subspace, or like you need this exponential dependence on the doubling constants in order to contain the whole space A, it can be covered by few translators of a subspace V of size close to the size of A. And the subspace V is essentially F2 to the n minus k times the all zeros. And it has been noted that efficient subspace cover in this sense is often enough in applications. You don't really need the set to be completely contained inside a single subspace, but only to have a few translates of the subspace that cover the set A. And then if you are very optimistic, you can make the following conjecture, which is called the polynomial Freiman-Ruja or PFR conjecture. It says that if A has doubling constant k, then A can be covered by poly k, some polynomial dependence on k, translates of a subspace V of size at most the size of the original set A. So this PFR conjecture gives a transition from a combinatorial notion of approximate subgroups, which is given by bounded doubling, to an algebraic notion, which is given by bounded subspace cover at only a polynomial cost, which is essentially the best you can do. And this conjecture has been extremely influential, and it has been shown to be equivalent to various interesting results on approximate structure, which I will now talk about. So some alternative versions of PFR. These ones, they concern more additive structure, which in additive combinatorics parlance, they're called Freiman homomorphisms. So you have this basic notion of an affine linear map. So a high dimensional map from F2 to the M to F2 to the N is affine linear if and only if, like this definition, it can be written as mx plus v, where m is a matrix and v is a vector. However, there are different ways of formulating exactly the same definition or exactly the same notion. One of them is given by Freiman homomorphisms. So it says that whenever we have this additive relation here, x plus y equals z plus w, f preserves this additive relation. So f of x plus f of y is equal to f of z plus f of w. And actually, one can show that this definition 2 is precisely the same as definition 1. And another possible way for you to define an affine linear map are those maps where this difference set, f of x plus y minus f of x minus f of y, where x and y, they run over the whole domain. This set has size 1, it's a singleton. And in this case, it will be the singleton V. And so those are three very different but equivalent ways of defining affine linearity. But then the interesting thing is that they give rise to different notions of approximate affine linearity, where we only require those conditions to be kind of almost satisfied. So essentially, we have a large constant or a small constant, whatever, k, let's say 1000. And so like the first notion will give this possibility for approximate affine linearity, saying that's like for a 1 over k fraction of the inputs, the function f is equal to a true affine linear function. This is an obvious way that you can say it's approximately affine linear. The other way comes from this condition 2. So it says that the conditional probability, when you condition x plus y equals z plus w, that f preserves this additive structure is at least 1 over k. And the third notion that we can get is that's like this different set, f of x plus y minus f of x minus f of y, is not necessarily a singleton, but it has bounded size at most k. And so this exactly equivalence notions give rise to different notions in the exact setting. This very different but equivalence notions, they give rise to exactly different notions in the approximate setting. And the question here is that are these approximate notions related somehow? And in fact, it has been shown that the PFR conjecture is equivalent to having polynomial relationship between these conditions. So to be more precise, there are uh, two results, each one of them equivalent to PFR. So the first one I call homomorphism testing. It says that if this probability of f respecting the additive structure is at least 1 over k, like this condition 2, then f agrees with an affine linear map in a poly 1 over k fraction of the inputs. So it's condition 1. That's now with 1 over k substituted by poly 1 over k. And this condition, this like homomorphism testing, is precisely equivalent to the PFR conjecture. And the other one where we say that's like if this different set has size at most k, then f agrees with an affine linear map in a poly 1 over k fraction of the input. So equating this approximate condition 3 and approximate condition 1, this is also equivalent to the PFR conjecture. So there are several different ways of you stating the PFR conjecture. And finally, PFR is also equivalent to the polynomial Gauss inverse theorem, which is perhaps one of the main reasons for why it's so important, because like this polynomial Gauss inverse theorem was a holy grail for additive combinatorics. Okay, so in order to talk about this, I have to define the Gauss norms. So we are going to work only with the Gauss U-tree norm, not the higher ones. So those are the Gauss norms that you consider. And you can think of them as being a local measure of quadratic structures for functions over the binary cube. So intuitively, what it does is that it averages a function over combinatorial parallelepipeds, where combinatorial parallelepipeds are exactly those points here, x plus a, x plus b, x plus c, and then so on, all of those that form a parallelepiped as in this figure. And then the formal definition is given by this, like the eighth power of the U-tree norm of f is given by the average over all combinatorial parallelepipeds of the product of f on the vertices of this parallelepiped. And this might seem like a very weird definition, but the important part is not the definition itself, but the properties of this norm and how it can be used to really study additive sets. And one way that you could go on about like seeing why this definition might be interesting is that they kind of mimic the linear dependencies of quadratic polynomials. So if Q is a multivariate quadratic polynomial of F2, then its sum over the vertices of any combinatorial parallelepiped will be precisely zero, because this is kind of a linear dependence given by the fact that Q is a quadratic polynomial. And if we put this into the definition, then we see that the U-tree norm of the quadratic phase function minus 1 to the Q is exactly 1, which is the maximum it could be given that the function is plus or minus 1. So it's bounded by 1 in absolute value. So it kind of gives a measure of if you are a quadratic, close to being a quadratic structure or not. And actually, the Gauss inverse theorem makes it precise. It says that if f is a bounded function over f to the n, and if it satisfies that the U-tree norm is at least a constant gamma, so it's almost as large as it could possibly be, given by the boundedness of this function, then there exists a quadratic phase function minus 1 to the q that correlates well with f. So the correlation of f with this quadratic phase function is at least some constants depending only on the lower bound of gamma of the U-tree norm. And the PFR has been shown to be equivalent to this this correlation bound here being polynomially related to the bounds on the U-tree norm. And this can be seen as a local to global phenomenon, where local quadratic behavior given by these local linear dependencies of quadratic polynomials, if this is satisfied approximately, which is measured by the U-tree norm, then this implies global quadratic correlation, meaning some correlation with a quadratic phase function over the whole domain. Okay, finally, I should say that recently-ish, so about 2.5 years ago, Gowers, Green, Manus, and Tao proves the PFR conjecture. So they showed that if a set A has doubling constant k, then it can be covered by a poly k, so some k to some power, let's say 100, translates of a subspace V of size at most as of the set A. And then, of course, all equivalent formulations are true as well. And now our question, which I think is a very natural question, is the following. Is it possible to algorithmize these theorems? In other words, can we find the hidden algebraic structures that are promised to exist due to these existential results? Can we find them efficiently? And what we did is, oh yeah, I should say here that efficiently means poly n time and poly n many number of queries or samples, where n is the dimension of the space. So the input will actually be of size 2 to the n. It will be a subset, so like the indicator function of a set will have size 2 to the n, or it will be a function, bounded function f, that has to have a value for all 2 to the n possible points. But we want to find it in time poly n, so polylogarithmic in the size of the input. And what we did is essentially that we answered this question in the affirmative. But the most interesting thing is that we did so by connecting it to a problem in quantum learning theory that I want to talk about now. Okay, to talk about this, we should first make a change in perspective. Because in computer science and combinatorics, we usually consider only bounded functions, meaning those that the subnorm, the infinity norm, is bounded by 1. And then we have this trivial but very useful fact that the U-tree norm is bounded above by the subnorm. It can never, if the function is bounded in absolute value by 1, the U-tree norm is bounded by 1 as well. And the extremises of this trivial inequality are, for real functions, they are precisely quadratic phase functions, minus 1 to the q, where q is a quadratic polynomial over f2 to the n. And then the direct plus inverse Gauss theorems says that the U-tree norm of a bounded function f is like a constant, is like almost as large as it could possibly be because of its boundedness, if and only if f correlates well with an extremizer, minus 1 to the q, a polynomial phase function. However, the natural analytic space of the U-tree norm turns out to not be L infinity as we consider in computer science combinatorics, but rather L2. And it's not really important what's written here. I just want to write something that gives the impression that the correct analytical space for the U-tree norm is L2, because this is the largest Lebesgue space where you can define the U-tree norm without caring about the dimension. So even for infinite dimensional spaces. And here it's like the largest because you are taking the expectation notation. So L2 is indeed larger than L infinity. And Einstein and Tao, they knew about this, the natural analytic space, and then they characterized the extremities of this inequality here, which is strictly stronger than the inequality that we had before. And then they showed that they are equal, these two norms are equal if and only if, well, essentially, if and only if f is a quadratic phase function supported on some affine subspace of arbitrary dimension. But there is a slight twist here that's like we have this kind of non-classical phase, quadratic phase function that we say that is important for our work, but it can be disregarded at first when first see it. But the important thing about this, why I wanted to write the precise formula, is that this formula corresponds precisely to the notion of stabilizer states in quantum theory, which seems to be a completely different area. And so, a posteriori, just because you know that those formulas coincide, we can define a stabilizer state, which is a notion from quantum information theory, as a function phi over f2 to the n, satisfying this equation. So the U2 norm is equal to the O2 norm, which is normalized by 1. And these stabilizer states, differently defined, of course, but in an equivalent way, they form a really fundamental class of quantum states, and they are very well studied. So some examples. The quadratic phase functions, they are always stabilizer states for any quadratic Q. However, we also have something very different, like for instance, the indicator function of a singleton, appropriately normalized to have L2 norm equal to 1. This will also be a stabilizer state, even though it's very far from being a quadratic phase function. And then a recent theorem shows that a quantum state has large U2 norm if and only if its stabilizer fidelity is at least polygamma. So in other words, like what it means is that if f is like say an L2 bounded function, so the L2 norm of f is 1, and the U3 norm is at least gamma, so almost as large as it could possibly be, with the condition that the L2 norm is 1. Then there exists a stabilizer state phi that correlates well with f. So the correlation is at least poly of gamma times the L2 norm of f. And so we see that learning a correlating stabilizer state is the quantum version of the PGI, the polynomial Gauss inverse problem. Because in this polynomial Gauss inverse problem, we get a function f which is bounded in L infinity norm, and we want to get a global correlation with a quadratic phase function, which is an extremizer of the L infinity equals U3 norm. And now we are in the L2 setting, so we have an L2 normalized function, and that has high U2 norm, and we want to get an L2 extremizer, which is a stabilizer state that has good correlation with the function f. So this is precisely essentially the same question, but in a different analytic setting. But the interesting thing here is that learning a correlating stabilizer state, is that this is a very well-studied problem in quantum learning theory, going back, well, at least as far as work by Montanaro in 2017, but probably further. And recently, there has been a breakthrough of Shen, Gongye, and Zhang, who designed an efficient quantum protocol to learn an epsilon closest stabilizer state to any given quantum state. So essentially, the result says that given like a linear number of copies, order of n copies of an n qubit quantum state psi, you can output very efficiently using a quantum computer a stabilizer state psi phi that has almost maximal correlation with psi, with the quantum states that you start with among all possible stabilizer states. And then an observation done by Yopriat and myself is that for bounded functions, meaning those bounded in L infinity norm, also not only L2 norm, we can efficiently transform a correlating stabilizer state phi into a correlating quadratic phase function minus 1 to the q. So it's essentially a rounding procedure that we make to transform the stabilizer states into a quadratic phase function that always works when the function we are considering is bounded. And with this, we can use this CGYZ efficient quantum protocol to give an efficient quantum algorithm for the polynomial Gauss inverse problem. So in this work, what we did was essentially to algorithmize the proof of equivalence between the polynomial Gauss inverse theorem and the polynomial Fermat-Ruja theorem, so that we can use the PGI quantum algorithm in order to obtain an efficient quantum algorithm for PFR. So we obtained the following results. Uh, if A satisfies, well, has doubling constant at most K, then there exists an efficient quantum algorithm that finds a PFR subspace, meaning a subspace V of size at most the size of A, so that A is covered by poly K translates of V. And here, efficient means like n cubed time, order of n random samples from A, order of n quantum queries to A. And one can show that like this amount of random samples and quantum queries is optimal up to constant factors. However, Jobriat and I also managed to dequantize the CGYZ stabilizer learning algorithm for bounded functions, meaning that we found a similarly efficient classical randomized algorithm that simulates the behavior of this quantum algorithm whenever the state we are given has amplitudes that are bounded in absolute value, essentially. And doing so, we can then obtain an efficient classical algorithm for PGI, for polynomial Gauss inverse. And then with our proof of equivalence, like our algorithmic proof of equivalence between PGI and PFR, we obtain also a classical version of the PFR algorithm. So there is an efficient randomized algorithm that finds a PFR subspace. And efficient here is just slightly less efficient. So n to the fourth time, n random samples from A and n squared queries to A up to log factors. And then again, up to log factors, the number of queries and samples in these algorithms is optimal. Okay, and also our algorithms actually, they provide an algorithmic framework that allows us to give efficient algorithms to the alternative versions of PFR. So as is written here. And these algorithms, as I said, they have a common core, just like the results themselves. So like these alternative versions of PFR or the original version of PFR, and to some extent the polynomial Gauss inverse problem, and also some other problems that are related, they all have a common core. So it's more like an algorithmic framework than one algorithm. And yeah, a perspective that you can see this is like an algorithmic local to global principle or efficiently finding hidden algebraic structure. But what I find most important about our work is that it makes explicit an interesting connection between additive combinatorics and symplectic geometry, which was very important in the construction of the algorithm. And symplectic geometry is known to be related to stabilizer states in the quantum learning theory. And so by passing through the quantum theory part of this, we make a connection between additive combinatorics and symplectic geometry that was actually first conjectured by Green et al. And this is explained on the new archive version, where actually we combine the two works that I talked about. So like our PFR work, which is like this talk, and the quantizing the CGYZ learning algorithm with Jobriat, and then we are doing a new archive version where we connect those two, where we like which will subsume both of them, and this will be coming soon to the archive, hopefully. And so hopefully by the time you see this video, it will already be on archive. And I think that this connection, it really deserves better investigation, and I really believe that it will lead to some interesting new results in additive combinatorics by applying this symplectic geometry framework. And I think I should stop here on this note. Thank you for watching.